All right, we're back on the air. So we're going to discuss frequency asked questions about resistance grounded technology. And we received a lot of questions. So what we're going to do is go over the questions, and we're going to try to get through as many of them as possible, but a lot of them are grouped together. So we're going to handle them as a group. So some of the questions we received were how to convert from a solidly grounded system to a resistive grounded system. A lot of questions about VFD and UPS compatibility, how to calculate charging current, VFDs on medium voltage, and there's a lot of questions on safety. So safety to personnel, elevated ground potentials, does that cause a hazard, and how to use high resistance grounding systems to reduce arc flash levels to below safe values, and ground fault detections. Some people wanted to know about the latest technologies, and we went on and on about the questions to discuss. So what we've done is we've grouped them together, and for the first one, we've how to convert from a solidly grounded system to a resistive grounded system, and we have a guest speaker for this, Aaron McPhee, who led his company in converting 100 plus transformers to high resistance grounding. Aaron majored in engineering and physics at Georgia Institute of Technology in Augusta Technical College, and Brno University. Received both his ASEE and BS degree. He is presently engineering manager with Graphic Packaging International, previously International Paper in Augusta, Georgia. Aaron is responsible for all aspects of power distribution throughout Augusta Mill, as well as manages the process control and reliability engineering department, and leads all E&I capital projects at the Augusta Mill. He serves as a corporate electrical engineering resource for GPI, as well as a member on numerous company electrical and reliability committees. He is also responsible for conducting EPD and instrumentation courses within the company. He has received awards and recognitions for his practical approach to EPD activities. And with that, I'm going to turn over control to Aaron, and he will go through his presentation and then come back to me.
Great, thank you, Sergio. Does everybody see the screen? Can I get some feedback?
I can see it. No one else can speak, Aaron.
Okay, gotcha. So, good afternoon, gentlemen. My name's Aaron McPhee. As Sergio said, I'm formerly with International Paper, spent many, many years with them. I've been in industry approximately 40 years, several different industries, and now I'm engineering manager at a large paper mill integrated with a cogen facility here in Augusta, Georgia. When I was first introduced to solid grounds many years ago, HRG systems, I had the same questions that some of you had, and I was fortunate enough to partner with I-Gard and Dr. J. Doss, and we developed some grounding systems that worked really well. And from a practical standpoint, I wanted to share some of the things that we encountered with the implementation of HRGs, as well as entertain some questions around it. Some of you had some real good questions that I saw towards the end of it. So with that, I want to kind of cover what we're talking about here and the impact to reliability and also safety when we implemented this across the fleet here. And what were the results? First of all, if I were to ask you, do you want seat belts, airbags, or would you rather have some kind of system to provide accident avoidance? Well, I would think most of us would say, look, I want to prevent things. I want to have accident avoidance. So let's talk about some of the codes around arc flash, as well as other protections that the employees need. NFPA 70E and also CSAZ 462, it primarily addresses the protection of personnel to minimize your personal injury due to electrical hazards. Now, some of those hazards, of course, are are the obvious, the nature of the arc being at 30,000 degrees plus, so severe burns, things like that. But there also is a lot of concussive action going on when the blast hits them. I got intimately involved. I'll tell you a story real quick, hopefully. It was Christmas Eve, and I was the mill manager at the particular time out here on weekend duty, and I just implemented hazardous categories across the facility. This was nearly 15 years ago. And there was a lot of resistance to wearing the PPE and understanding, the hazards that are really involved with it. And I was coming in on weekend duty. It was Christmas Eve, and I saw one of my new employees walking up the steps to a motor control room, and he was carrying his 40 cal suit. And I thought, wow, that's awesome. The guy took it to heart and he did it. I didn't think anything of it. I went to my desk, started getting ready for the morning meeting on the weekend. And then I get a call from the area manager in the pulp mill. And he says, listen, one of your employees has been involved in a severe blast up in the motor control room. You need to come now. Boy, I'll tell you what, my heart just dropped right then. And you can imagine all the thoughts that came into my mind. The first of which, here it is Christmas Eve. Is he going to have a Christmas? Was he hurt? What about his family? What about his children? And it really sunk in. It really brought it to home with me how important this is for us when we're designing systems or trying to improve them as we can, to make it a point of providing the best protection, whatever methods we're using, but also to look further beyond just one method and to consolidate a bunch of things to make it the best you can for these people. Well, thankfully, as I went up there, went up the steps, the guy was shaken up. The employee was sitting against a low voltage motor control center. It was a 480 volt center, and it was just a hazardous category 3. And he was about to cry, and he was definitely shook up. And I looked around the room. Of course, there's smoke all over the place. It was just a size 1 starter that actually had a bolted fault. When he was pulling it, the back of it was really compromised, and it arced so bad it cast his shadow onto the MCC behind him. So when he moved off the MCC, I could see the outline of himself, and I could see all the copper plasma embedded in his 40 cal suit and all. So yeah, it's important. It's important what we do as professionals in our crafts, and it's important to make sure that we keep that on the forefront when trying to build a system, modify a system, et cetera, and so forth. So, NFPA 70E in the United States, of course, covers the protection of personnel, and the latest rev on 2018 has had some pretty good changes as it's developed over the years. Well, what else should we be doing other than protect our people? What should we do to protect our equipment and people? Well, you got to do safety by design. Many of you have heard that before. Of course, you design the safety in as we're building stuff and designing stuff and engineering stuff. So we eliminate the injury potential from the start. That would include maybe some arc flash rated starters, I-Gard starters, metal clad switchgear, grounding methods, direct blowout switchgear plenums, things like that, remote racking so the employee doesn't physically have to be in the boundaries of the arc flash and the incident energy that may happen. And you could also employ engineering controls to minimize the potential of electrical incidents. For instance, maintenance switches, tighter coordinations. We call them maintenance mode switches, that you would activate if you were interacting with the equipment and taking it a lower instantaneous current while you're interacting, so the incident energy is reduced. So that's something you can do. And most of you guys are familiar with all of this. The other thing that can be done is, well, what about high resistance grounding? How can that help protect not only the employees, that guy on Christmas Eve and his family, so he got to go home on Christmas, and also protect our equipment, which means that we're viable as a company making a profit. OSHA, and this is typical across the world, your hazard control measures, right? There's a range of them. the first of which, and the lowest, of course, is personal protective equipment. The next is administrative controls. Hey, I check a sheet, I sign off, I said I did this and all that. The next is warnings, putting warnings on there, don't do this, don't enter this, don't do that. And then you get into higher levels of engineering controls, substitution, and total elimination of the hazard is where we really want to be, if we can be at all times, to protect everybody. So here's a different look at it, and that's what 70E does, as well as the ANSI standards. Elimination, substitution, engineering controls are your top tiers, and then your lower tiers here. And where are they addressed? Well, PPE, it is addressed in 70E tables, and NFPA 70E addresses basically your warning, your admin controls, and your PPE. What it doesn't really address is the elimination, substitution, in your engineering, your design. To really have an electrical safety program that's very, very, very good, you really need to include all of it, not just stop with 70E and PPE and admin controls. You've got to look beyond that to, is there a way I can eliminate it? Is there a way I can do substitutions instead to reduce the hazard or put in engineering controls? 70E says, and this is the new 2018 version, it's a little different than the previous one. They say high resistance grounding will insert an impedance into the ground return path and will typically limit the fault current to 10 amps and below at 5 kV nominal or below, leaving insufficient fault energy and thereby helping reduce the arc flash hazard level. Wow, there's a statement. We've finally come to a point where enough studies and enough incidences have happened that we know that by putting a high resistance in the grounding, you are absolutely eliminating the fault currents on the first fault. And I'll get into that in just a second here. The Canadian standards, Z462-08, also has a note on it. It says high resistance grounding, low voltage 5 kV nominals are techniques available to reduce the hazard of the system. So both organizations have now taken a stance that says, yes, this is a method to do it. Let's talk about 70E. In 70E 2018, there's a couple things. They say employees interacting with energized electrical conductors and circuits can be exposed to unacceptable risk of injury from electrical hazards. This exposure can result in, like I was saying earlier, you've got shock, electrocution, arc flash, thermal burn, the molten metal, like I explained with the copper plasma, the shrapnel, and pressure blast. And you can also have secondary injuries, knocking them off a ladder, their physical reaction of avoiding the hazard could put him at risk by jumping off a platform or running into something, those kind of things. 70E addresses electrical safety work practices, safety-related requirements, and other admin controls, like I said earlier. Now, there's actually three in the United States, three standards that defines, and they're independent as a whole for electrical safety. The first is NFPA 70E, which is what we call the National Electrical Code. Well, that defines safe electrical installations. So all your different fusing and breakers and loading and protections and all that is NFPA 70. NFPA 70B defines the recommended practice for electrical equipment maintenance. Now, why is that important? Well, that's very important because if you are basing your design and your system off of coordination, you have to take into account that breakers that may be 50 years old, 40 years old, 60 years old, and all these clearing devices actually function in the 5 milliseconds they need to or less and provide the current limiting that they're designed to do. If you're not maintaining them, then all bets are off. You can do 100 studies and not maintain your equipment, and you're not doing yourself any justice. NFPA 70E is the third standard that says electrical safety in the workplace. It defines the practices. How is the electrician, the electrical engineer, to be protected? What are some of the things he can do to stay out of the line of fire, to stay at least safe where he's not getting anything more than a second-degree burn should something terrible happen. How do you do that? And what are the policies and procedures and administrative stuff that has to happen? So all three of these, I often hear people reference, well, I comply with NFPA 70. Well, okay, do you comply with 70E and 70B? Because they all make what we call is one safety electrical system. It's design it right. What do you do? It's 70B, maintain it right, and 70E, when you have to interact with it, this is how you can do it safely. So those are your mitigation standards. Well, the minimal that we do and should be doing are 70, 70B, and 70E. The best automatic reduction of risk, all the above, and like I said earlier in the OSHA hazard assessment, you need to eliminate or reduce the risk through engineering, design, and controls. And that's the extra step that can be taken not only on new greenfield projects, but also in substations and systems that are many, many decades old. There's a lot of improvement that can be made so things can be safe. So let's talk about ground faults. Typically when a ground fault happens, there's lots of documentation that says between 80 and 95% of all electrical faults primarily initiate as ground faults. So if you can limit the magnitude of the ground fault, a great majority of all phase-to-phase arcing faults can be eliminated. What that says is usually the faults happen from phase to ground first. Then they propagate into a phase-to-phase or a phase-to-phase-to-phase, which is the worst, right? So if you can eliminate the inception of these things, then you have a higher probability based on all the documentation, 80 to 95% of eliminating a lot of these catastrophic blow-ups, failures, equipment damage, and things like that. So informal numbers, less than 1% of the faults are initially start as three-phase faults. So there are situations where that happens. People leave clusters on, jumpers left on, water entry into the system or the bus systems, but less than 1% of the faults are in that category. The majority of them start off as a phase to ground fault. So by knowing that, then one would ask, how can we eliminate hazards if we know when they first start, the majority of them? What can we do to put the engineering designs and controls in for that situation? That eliminates the probability of both equipment failure and employee failure. Not failure by an employee, excuse me, the employee getting hurt. So let's talk about high resistance grounding. Does it really work? Does it reduce unplanned system outages? And does it reduce the potential of arc flash hazard? Those of you that are familiar with it would say yes, it does. But only if the neutral grounding system integrity is maintained. So that brings into another design question into play. We can throw in a high resistance ground and have it unmonitored. And how do you know that the resistor is even good? 24 hours a day, 7 days a week, you're relying on this resistor or this impedance path to provide you that low current fault. And how do you know it hasn't shorted, or how do you know it hasn't blown open if you haven't monitored it 24/7? So we'll get to that in a second, but it's very important that you have to maintain your system, and in my opinion, you have to be monitoring your resistor. And monitoring it isn't, hey, I'm doing rounds in the MCCs every 1 month or 2 months or 4 months. That's good, that's better than nothing. But it's only good for the amount of time you're standing there looking at the resistor. So when the first fault happens, we also need to clear it before the second fault happens when you have an HRG. So that's real important. You need to make sure that your resistors are maintained and that you clear your faults, your phase to ground faults. Always clear them as soon as you can, because if a second fault happens, then it can be catastrophic. Let's look at a solidly ground system. In our particular systems, we were majority solidly grounded across our cogen facilities. And this is just the atypical with the three-phase transformer. with your voltages of 480 volts phase to phase, 277 line to ground, and your load being represented here as ABC here. Now, when one of those phases, let's say C, goes to ground and makes its way back to the Y, the center point of the Y of the transformer, ours are delta Y transformers, you stand to see at least, and could be up to 30,000 amps. Now think about that, 30,000 amps. That's a tremendous amount of energy that's coming down anything that's structural, conductors, number 4 wire, 4-aught wire, whatever, that is significant. And if it goes on for very long, if you're not clearing immediately, then you're going to have some damage. And you're probably going to have some damage anyways at that kind of amperage, because things are just not rated for that. It's rated to withstand it, but not rated to conduct it. So what are some of the pros? Well, a solidly grounded system has a low installation cost, has immediate isolation of a faulted system, but the caveat there is, A, everything's properly coordinated, and you've done your due diligence by doing your maintenance on your breakers, and you're coordinated properly, and you're not overreaching when the fault happens and taking down more of your system than needs to be. It does provide for voltage stabilization across the network. It allows the use of a neutral for single phase loads. So if you were wanting to take this into a transformer, yeah, sure, you could have your neutral to line loads, your single phase loads. There's definitely a visible detection of your equipment. Where is it faulted? Well, there it is. It's burnt up. You can see that right away. And the equipment insulating rating, phase to ground voltage, is based upon the phase to ground, which in that particular case that I just showed you, the 277 rating, okay? What are some of the cons to solidly grounded system? Well, first of all, 30,000 amps, there's a lot of personnel dangers when they interact with the equipment. You will have some unplanned outages. Things will go down, and they'll go down when you least want it to happen. 2 a.m. in the morning or 5 o'clock in the afternoon on Friday, it's going to happen. So you have no idea when it's going to happen and when it does, and it just catches you off guard, as well as it upsets your whole operation. You will have voltage dips, transients during fault. You imagine that 30,000 volts coming down the line under a faulty condition, it's pulling your whole bus system down, everything. High arcing currents. You have electro equipment damage. You all have seen that if you've been in the industry for very long. When a fault happens on a solidly grounded area, it's pretty impressive, even when you're coordinated. Fire hazards, another one. Remember, you're introducing that arc, that incident energy of that 30,000 amps, let's say, in the case of that, and you got 30,000 degrees. You're apt to catch things on fire. I've seen it when we had a fault in our bus system and had a poorly grounded breaker on a 15 kV breaker, poorly grounded. And the fault actually found another path over a roll-up door in the basement of a powerhouse that had bark buildup, and all of a sudden the bark caught on fire. So it's highly likely, if that were to happen, that you would have a fire. Even combustibles in the area would catch on fire if you had them in there. And the biggest thing is, of course, the personnel dangers, but also you have high repair cost and time it takes to get back on your feet. Well, let's talk about a resistance grounding system. Now, remember we talked earlier about, engineering controls, what can we do? Well, what if we were to take the Y of the transformer and just put a ground there, just like we did, but also add a resistor? So we're going to limit that current, that fault current, should a feeder go to ground, and come up through the resistor and go back to the Y. We're going to limit that. All right, now that includes the feeder capacitance and all that, but let's just say for simplicity, you've got a fault to ground, goes through the resistor and comes back. Well, we can control the resistor. So your IBS of F, we can absolutely take care of that and limit it to only 10 amps or less. Now think about it. If you had a choice, I have a fault and I only have 10 amps That's a whole lot less arc flash, minimal to none, and a whole lot less personnel injury and a whole lot less equipment damage, on and on and on. And with such a low fault current, you can stay running. Now, there's the magic in it, and we can talk about that later. I'll let Serge tell you about that if it comes up. But you can have a faulted phase and on a three-phase 480-volt motor, and the motor continued to run. It's really interesting, and it has helped us. We are a 24/7 facility, 7 days a week, and for every hour of downtime on our machines correlates to $30,000, $30,000 an hour, and so it's pretty significant. So if we have a fault, let's say it's just a little heater or a three-phase motor or something, previous to HRG installations, we would have low voltage power circuit breakers trip off. And then that would cause some incidental piece of equipment that was important that was interlocked to the machine and shut the whole machine down. So we were able, and we've had several incidences where this has actually saved the machine till we had the ability to shut down on an outage scheduled within a very short period of time and then fix what we had without interruption to the operation and without anybody getting hurt. So what are the pros and cons of impedance or resistance grounded systems? Well, it reduces unplanned outages, just like the example I gave you. Transient stability of the system. Can you imagine 30,000 versus 10 amps? That's a big difference, right, in what your system is actually seeing. It eliminates undesired voltage dips. So where you would have seen a pretty significant voltage dip, and especially on the higher end of your supply, if that were to fault, you'd see it pretty significant, which would ripple across your bus system and more than likely take a lot of that out as you segregate or island your different bus systems and all. Now you're talking 10 amps. It also allows for fault detection of the faulted equipment. What do I mean by that? I'll tell you about that in just a second. And it minimizes arcing current. So your arc flash hazard is reduced significantly. What are some of the cons? Well, your initial investment is higher, of course, because you have to purchase the HRG and you have to install the HRG on either new equipment or on retros that you're doing. Fault detection and removal is required. As I said, once the fault hits, you need to go after that first phase to ground fault, because when a second fault happens, it's really catastrophic at that point. It's just like if you had a solidly grounded, or even worse. System integrity maintenance, that's required. So that's a con. There is some maintenance required on an HRG system. You have to make sure the resistance and the resistor is in sound condition and the unit is on and it's connected and it's serving its purpose. And also equipment installation. The installation rated for the phase-to-phase voltages is higher. So if you remember if you remember the drawing I had here, you know, when you have the C phase goes to ground, and if this was on an HRG system, you would actually elevate two of these phases to a 480 volt to 480 volt to ground potential, while C raised up. So it's important, right, that you understand that the insulation in your system is stressed also. Not only do you have to fix it because of a secondary fault, but you got to fix it because you're stressing your old insulation in your cabling, in your bus systems, in your standoffs, in your breakers, all that. So it behooves you to get in there and fix it as quick as you can. So failure modes, HRGs, what do we do? All right, over here, there's a drawing of an open circuit, right? The middle is an open circuit, and the right-hand side is the HRG in service there with a short circuit. So if you had and weren't maintaining the resistor, what would happen? Well, you'd have an open circuit. You'd have an ungrounded system. So basically, when you have a fault on this phase, right, you have an ungrounded system. You have nowhere to go. And you guys know the issues with an ungrounded system when something like that happens and the potential risk it puts people at. Open circuit, when you have this, it's the same thing. This would be a medium voltage system. You would put it through a high inductive transformer, and then you would create resonance. And Serge can talk more about that if that comes up. Short circuit. You could have where the HRG is short circuiting and say it's going around this resistor. That's possible. If you're not maintaining your resistance in your resistor and looking at it and making sure that you're monitoring that resistance is sound, then you could have a short circuit and you're back to a solidly ground system again. Okay? So the main thing is to avoid the second fault. And I talked about this earlier. In one of the phases, typical Y, one of the phases, let's call this C, goes to ground, then you would have this elevated voltage on the other two phases in reference to your ground. And that's just a vector diagram explaining that. Hopefully that does that for you. What you don't want is once it's grounded here for another one to go to ground, because at that point, the HRG doesn't come into play anymore. Now you're feeding phase to phase. So let's talk about how do you know if the resistor is good, bad, indifferent? So there's several ways of doing it and several designs. Typically, what's done is you actually either put a sensing resistor in or you split the resistor and you monitor the resistor online all the time. And you have a system that's monitoring the resistance and it's generating its old high and low resistance at a maybe 1 second cycle, 2 second periodicity, so that you always know that state change in resistance, your resistor is good. That's real important to know that your resistor is in service and it's always working. Otherwise, the unit needs to alarm. And the unit needs to alarm in a manned location if you can, because how many times have we put alarms in motor control rooms? We have nearly 300 of them here. And by the time somebody gets in that motor control room, it's days and weeks later and recognizes there's an alarm. So be thinking about manned locations when you deploy stuff too for alarming and safety. That's important. So risk reduction. Well, the key point in 70E 2018 and 462 is let's reduce the risk. All right, risk is equal to frequency times your consequences. So if that's the case, the use of HRG does in fact reduce the probability of frequency, and then thus reduces the risk of an arc flash event, which could hurt employees and shut down operating equipment. So that's real important, that deploying an HRG, it sounds kind of odd. You're putting in a higher resistance, but in fact, it actually helps. It helps tremendously with employee safety, and it helps tremendously with maintaining equipment and being able to have orderly shutdowns when you have a fault. And it's not taking you down, like I said, at Friday afternoon at 5 o'clock or at 2 a.m. in the morning. So let's talk about it. Does an HRG reduce the incident energy required to be put on the label? Well, not really. So when you're doing your studies, and many of you I'm sure have done your arc flash studies, the labeling for your HAZ category is based off a three-phase bolted fault. Okay, so it doesn't reduce your label. However, like I said earlier, it does have a higher probability of incident energy reduction of 80 to 95%. And you can use that in your risk analysis now. So with NFPA 70E 2018, it's a whole new concept in there of allowing for risk assessment. And that comes into play as you're designing or retroing stuff as well. So what do we use, an HRG or a solidly grounded system? What do we use? Well, you need to consider your safety, your cost, and your benefit, of course. That's with everything we do. And the impact on failure to the system. Can we shut it down immediately? What's the cost of a shutdown or a planned or unplanned outage? What are your maintenance practices? Are you maintaining your equipment like you need to? Will you maintain your HRGs like you should? Do you have monitoring of your resistors like you need to? Is there any environmental conditions you need to consider where you're deploying this? And of course, as everything we do, is there liability considerations, of your particular design? And the last slide I want to show you is some data taken from about 2003 to 2016 as we were deploying the HRGs. Basically over here, this is the sum total cost of motors, motor failure impact, and basically this motor cost was how much does it cost to rewind a motor and how much downtime we incurred. I did find out from taking this data and looking at it over a period of this many years, when a motor faulted, there was significantly less damage within the motor, and sometimes you could just get away with bacon dips and you're up and running, and maybe some the regular T-lead rewinds and you're up and running again, versus a total restoration, rebuild, bearings damage, etc., and so forth. So you can see about 2011 is when we started deploying HRGs. Prior to that, in 7, 8, 9, 10, we started having significant motor impacts. And during this time is when we decided we're gonna change how we do things. And we started deploying HRGs the first year, the second year, the third year, and the fourth year. And these motor failures actually that actually cause these higher levels than normal were actually due to substations as we were deploying these HRGs that weren't HRG protected at the time. So they caused a little bit of impact. But right now we're still on this trend of very, very little or minimal motor costs due to faults and all. So with that, I hope I've explained a little bit about HRGs, what we've done, why I think it was a good move on our part to deploy these things, and also it was a good move, and I don't work for I-Gard, so Serge, don't say anything, but I really did partner with I-Gard, and so did Jay, to kind of develop their resistive systems to a point where we have network capabilities on them, as well as resistor self-checking, as well as really a lot of the reliability aspects of the HRG installation they've incorporated, and they were just fantastic to work with. So I'll give you a little plug there, Serge. And with that, I'll turn it back over to you, Serge.
Thank you very much, Aaron. That was very good. Just while I'm switching everything over, do you what was the methodology of converting everything over, or what was the driving force of converting 100 substations from solidly grounded to resistance grounded?
The major driving force was reliability and personnel protection, both. So as I said, it was near and dear to my heart with the employee on Christmas Eve. Do you have control yet, Serge?
I'm trying to get it.
You should have it.
I believe I have it now, yes.
Okay. So it was near and dear to my heart, that seeing what that copper plasma really embedded in his 40 cal suit and the shadow it was casted, and this was only on what we call a category 3 or a HAZCAT 3 MCC. I started rethinking how we did business out here and why we were doing it, and started educating myself in particular of there's got to be a better way to do things. And that, coupled with reliability tracking of downtime and incidents and all that, has included, I came to a really quick conclusion that something had to change. Something had to change for both the equipment and sustainability of the mill, as well as the employee safety.
All right. I don't know if we're going to have time to do some of the other things here, but maybe I can just ask you some questions. Did you have any difficulty, Aaron, when you converted with your compatibility with variable frequency drives or adjustable speed drives?
There was some. Basically, all vendors will supply you the VFDs and or the UPS systems. We have many of them, as you guys can imagine. They will supply you a design on the front end of those units that are HRG compatible. And even if you have an existing one, you can go back to the vendor and say, look, I'm putting in an HRG. What do you guys have that I don't know about that's not shown on the prints on the front end side on your filtering? Do you have MOVs? Do you have anything on the front end? And everyone we've worked with have said, hey, you're good to go. We haven't had any that we turned the HRGs on and we lost something or had issues.
Right. And if you look on the screen, you can see the front end. A lot of people put MOVs on the front end and EMI capacitors. So basically what some drive manufacturers believe is that ground is this miraculous place that can just absorb all unwanted frequencies.
Yeah, that's not going to happen.
And the MOVs are there so that you can protect the drive, so they would actually perform their job if you have an overvoltage. But with the resistance ground in the system, you're going to go to line potential with respect to ground when you have a fault on the system. So you mentioned a couple of things. One was be very careful and clear the fault as quickly as possible, because if you have that second fault that comes in, it can be very dangerous. It's like having a solidly grounded system and having your fault on the system, and maybe a little bit higher because you do have a phase-to-phase fault, phase to ground to phase.
Sure.
We do have relays that will protect you against that as well, and automatically shut off the feeder that is of lower priority. I know you didn't put that one in, but it was under some consideration as well.
Yes, sir. So that's like Sergio said, that's another level of design that we weren't able to fund, that we wanted to put in those relays for that, and then do some coordination tripping to eliminate that as well. But we chose to go ahead and rely on the breaker tripping and get the instantaneous as well as the long time down to a minimal level of a Cat 4 or less, preferably a 2 or less on most of ours. So a big coordination undertaking we took on at the facility to get there.
And did you do charging current calculations on your substations?
You know, I can't remember.
Typically, what were the size of your substations?
Well, the typical one was 1,000 kVA to probably in the neighborhood of 27. Those were the low voltage ones. We have a few, of course, that we got from you guys on medium voltage as well.
Yeah.
That were higher than that. Were 5,000.
Okay, and part of the package that you got was with the resistor monitoring as well, and it just so happens that in Canada, that's now in the code, and if you put in a resistive grounded system, you must have resistor monitoring.
Fantastic.
Which also, not only does it take care of the open and shorted resistor, but for some reason, they've allowed resistance grounded systems on a distributed neutral network. So if that neutral ever becomes grounded anywhere in the system, you have to isolate the system right away. And we have to look at the conductor between the neutral point of your power source to the resistor. If that becomes open or shorted, we have to isolate the system.
Yeah, those are all great things.
And there was some question about safety to personnel. Would you say a resistance grounded system was safer to personnel?
Oh, yes. Oh, much safer. We've had several incidences, as you guys can imagine, when you have, 60 some odd E&I guys. E&I we call electrical and instrumentation. So you have 60 electricians, always working around the clock here. There are going to be some accidents. And we've had several events where they've dropped a screwdriver or a wrench. They were working live with a hot work permit and everything, and still something happened, and that action resulted in hardly anything. They just kind of look at you and go, wow. If that would have happened 5 years ago, it would have just blew up in my face. So one of the things we do for training, we want to make sure that they demonstrate, right, functional knowledge of an HRG system. So we have an annual training. It's a short class as part of all the NFPA 70E training they have to take and all, where they actually go on to a live 480 volt, and we energize one of the phases. It's an HRG system, and we energize a phase, and they actually take voltage readings and see that it's very minimal as far as an arc flash. You don't even see it. You just have the alarm go off on the HRG.
Okay. And the elevated ground potential, because when you have a ground fault, the two unfaulted phases elevate to full line-to-line potential with respect to ground. You mentioned a couple of things. You mentioned that the insulation is going to be higher. The insulation should be higher on that cable, but in actuality, there's enough insulation put in the resistor, or put in the cables, to more than exceed the electrical dielectric, the extra potential that's there. So
in practicality, it's 600 volt rated usually.
Yeah, and that usually doesn't become a problem until after 5,001 volts.
Yes.
Another question that we had was how does high resistance grounding reduce arc flash levels to below safe values? And you touched upon that. It doesn't. Employing a resistance grounded system does not lower incident energy. It only reduces the probability or the risk of having a fault propagate to a phase-to-phase or three-phase fault. As you said, all the other mitigation techniques that you use, the maintenance switch, differential protection, zone selective interlocking, they only come into effect after the fault occurs. Resistance grounded system is really the only thing that comes in that helps you before the fault occurs. So it's like a early warning system. We've had some questions come in, and one guy said, well, we didn't discuss adjustable speed drives enough, and that's only because we have a shortage of time, and Aaron was presenting. So what we're going to do is we're going to have a dedicated presentation, I guess, on the variable frequency drives or adjustable speed drives to properly go over the compatibility issues with them, because it does take some time. And we might discuss how to calculate charging currents. We've had a lot of people asking questions about that as well. Jessica, can you think of any other questions to ask?
I just wanted to say that we will be releasing a question and answer document after this webinar. So if you didn't get the answer to your question, be sure to keep an eye out on our website for the answers to all of the questions asked during registration and during the live webinar. And also, this webinar is recorded, and you can find the recording within 24 hours on our website as well. So we've been getting a lot of questions about that. Can you discuss the application of HRG on the 480 volt secondary of a Y delta transformer?
I'll get that one, Aaron, if you don't mind. With a Y delta transformer, you're obviously going to have to create a neutral on the delta side, and there's many ways you can do that. I assume the delta side is a secondary and the part that you want to put the resistant grounded system on. So you'll have to either create a neutral with a zigzag transformer, a Y grounded delta, or a Y grounded open corner delta, and each one of these will limit the fault current, and you may employ resistance grounded system at that point and treat it like a Y system.
Thanks, Sergio. One more question. What is the recommended surge arrestor for solidly grounded and resisted grounded systems.
Aaron, did you have any TVSSs on your system?
No, we didn't.
Okay. On low voltage, typically the surge is addressed by TVSSs, or transient voltage surge suppressors. And for resistance grounded systems, you should employ a TVSS which has been listed and approved for use on a resistance grounded system, and they do have them. What you have to do is specify to whoever you're buying your TVSS from that you want it a TVSS for a certain voltage, let's say 480 volts. You want to handle 200 kA of current, and this is the type of grounding system you employ is a solidly grounded system, a high resistance grounded system, a B-phase delta grounded system, or a delta grounded system, which is an ungrounded system. You have to specify that to the person or to the company that is going to supply your TVSS, and then you will get the correct TVSS. Typically what happens for TVSSs is they will perform their job if you have a ground fault on your system and it's not compatible with that resistance grounded system, because the voltage on the two unfaulted phases will elevate to full phase-to-phase potential, causing those MOVs to collapse. And now you have a three-phase short. And I've seen a lot of these because people don't use the right TVSS, and all the smoke comes out of the TVSS, which is not really a fun place to be.
Thanks, Sergio. Another question, is there an industry standard for stating breaker tripping priorities? For example, always trip, never trip, etc.
Always trip, never. For priorities?
Yeah, so is there an industry standard for how you should be setting your breaker tripping priorities?
If you were going to employ our DSP system where it has second fault priority trip, it's not the breaker that makes the determination, it's the load that's connected to that breaker that makes the determination. So if you're in a hospital and one of your breakers is feeding an operating room, you obviously do not want that to trip. So you're going to set that as the highest priority. So that means if you get a ground fault on B phase of that breaker, and then you get a fault on A phase on another breaker, the breaker that is servicing the A phase fault will trip first, and the B phase fault that's feeding the operating room will not trip. And if you set it as the highest priority and you have a catastrophic problem, it will always be the one that's in service. Similar if you have a data center, chillers, air conditioning units are very important, so they will always have a higher priority. So there's no real standard as far as the breaker is concerned, but it's more the load that the breaker is serving.
I'd like to comment a little bit on that just for a second,
Sure.
Sergio. And so what Sergio was saying was exactly right on point. The actual life safety portion of it, that's the first thing and foremost, that's your highest priority, right? If tripping this breaker is going to negatively impact life safety, then that's the breaker you definitely want to save for last. Equipment protection is the next level up, and this is common, like the several examples he had. Another one would be like turbine lube oil system for a 3600 RPM, 15 kV, 40 megawatt, 50 megawatt turbine. You want to run to failure on those things, but by running to failure, it doesn't wreck anything. But if you trip the lube oil pump, what happens? You're going to wreck the whole turbine. Possibly it runs away with you. Possibly you have an explosion. So you have to consider all those things, but life safety is definitely number one. Thank you.
All right.
Great, Darren. Go ahead, Sergio.
Well, again, I just wanted to repeat that, Jessica, we should probably have another one of these sessions to address some of the questions that have not been addressed. And I noticed by the questions coming in that people weren't happy with me not addressing them.
Well, we can definitely schedule another webinar to address the questions that we haven't had a chance to answer yet, and especially the questions that have been asked several times, like you said, about charging current calculations and VFD compatibility.
Right, and if there are any other questions that you want to know more about, please send them through to us or Jessica, and we'd be happy to address those in an upcoming webinar.
Absolutely, yeah. You can keep submitting your questions right now in the GoToWebinar platform, or you can email jcraig@i-gard.com with any other questions or topic requests. If you do have any questions that we haven't had a chance to answer, make sure you take a look at our other webinars that are on www.i-gard.com. We did approximately 8 webinars in the past few months, all on different topics, and it's all relating to HRG, of course, so you can probably find quite a few answers in those videos. As well, there's a Q&A that correlates to every webinar with all the questions and answers, even if it's not in the recording itself. And with that being said, I think we're at the 3 o'clock mark pretty much, which is the end of our scheduled webinar.
Thank you very much, Erin. Thank you for your time. It was a great presentation. I'm sure people learned a lot about your experiences. And most of all, Erin, I want to stress that you probably saved enough money that paid for your HRG system with all the motor repair costs that you wouldn't have to spend.
Yeah, that's in downtime. That's significant. Yeah, if you were to throw the downtime in on the machines, it's pretty significant here. So I want to thank everybody for listening to my simplistic view of what's going on. I'm more of a practical guy out here in the field. Certainly, if you have any questions about HRGs, Sergio is the guy to run them through. But if you want to contact me through him, that's fine too. On real world applications, you know, there's questions I've gotten like, you know, how do you mount the CTs? Well, your CTs need to be mounted on your secondary as close to the transformer as possible. And then, you know, what kind of structural arrangements do you need to have? You know, these are things that you need to consider when you're doing protections on your substations, not just HRGs. But thank you very much, everyone.
Thank you, Erin, and thank you, Jessica. And that concludes. Please, Jessica will send out an email to everyone that's attended and provide a link to the recording and send out the questions and answers, as well as post any upcoming webinars to complete answering the questions that we didn't get to yet. We had a lot of really good questions come in, and some people even signed in with practical questions with single line diagrams. Well, what would you do in this situation like this? And those are always helpful because that helps everybody understand. Again, thank you very much. Everybody stay safe. Thank you very much.